Hey guys, so this is just this week's video of the questions we ran through last week. I'll jump right in. So we covered a bit of algebra, a bit of inequalities, and a bit of logs. So yeah, let's jump right in. So right at the start, I just want to go back on a bit of algebra, just because this is a useful trick to know, and we'll see why now after this. But well, the trick comes from question 2 on, but let's just do question 1 and get it out of the way. So this is just to kind of remind you, because it's an important part of algebra. It says determine the values of k for which the quadratic equation, this quadratic equation has real roots. So we know if it has real roots, well, if we're trying to determine anything about the roots, we know we're dealing with the discriminants. That's b squared minus 4ac. And we know this comes from our roots are going to be minus b plus or minus the square root of all this over 2a. And so how we're going to determine that it's real roots is if based on what's underneath this square root sign. So if what's under this square root sign is less than 0, then you're going to have the square root of a negative number. And that's a whole different topic that's called complex numbers. And we haven't touched that yet. So just know if it's less than 0, then it's going to be unreal. And we want real roots. So obviously we want greater than or equal to 0. Because if it's real roots, it can't be less than 0, so it has to be greater than or equal to. But you see here this s, so we want two roots. If it was equal to 0, all this would be equal to 0, and we just have one value for x. But we want 2, so we want to include this plus or minus, and that's attached to the square root here. So this has to actually have a value. So that means if we want real roots with an s, it has to be greater than 0. So b squared minus 4ac greater than 0. And we can just sub straight into that. We know our a here is 1. Our b is going to be minus 3k minus 1. Or I can even leave the minus outside. Minus 3k plus 1. And the c is going to be 2k squared plus k plus 4. So let's sub in. So this is minus 3k plus 1 and all that to be squared. So I'm just subbing that in for b. Then we're going to do 4 times a is 1 and c is this here. So when we square anything, if it's a minus number, it's just going to become positive because a minus times a minus is positive. And we can just then square our bracket like this. And then we're going to multiply this 4 in. So 4k squared plus 4k plus 16. And all of this, we were saying, had to be greater than 0. Oops. So 3k plus 1 squared, we know how to do that. We're going to square the first twice, then multiply together, and then square the last. So 3k squared plus 2 times 3k times 1 plus 1 squared. And then we can multiply in this minus 4k squared minus 4k minus 16 greater than 0. So 3k squared, that's going to be, you can square the first and square the second. So 9k squared, 9k squared plus 6k plus 1. 1 squared is just 1. And then minus 4k squared minus 4k minus 16 greater than 0. So 9 minus 4 is going to be 5k squared. 6 minus 4 is going to be 2k squared. Or just 2k, sorry. And then 1 minus 16 is going to be minus 15. No, that's greater than 0. Sorry, I just made a mistake there. So when we multiplied in this 4 in here, so 4 times 2 is 8. So all these 4's changed to 8. And then everything else was right. So I'll change all them. And then 9 minus 8 was just k squared. So then if we're factorizing this, that's just k times k. 5 times 3 will do. So 5 times 3 is 15. And then 5 minus 3 is going to be 2. So 5 minus 3. So k plus 5 times k minus 3 is going to be greater than 0. So this is when we split it up into some cases. So if we want this whole thing greater than 0, we want this whole thing to be positive. So both of these multiplied together have to be positive. Now, there's two ways that can happen. That can be case 1, if this one is negative and this one is negative, then a negative times a negative is positive. And case 2, first one is positive and the second one is positive, and then a positive times a positive is a positive. If we had another case where it was this one was positive and this one was negative, that wouldn't work because a positive times a negative is a negative, and we want the whole thing to be positive. So any case where they're both different from each other, that wouldn't work. So we only have two. They're either both negative or they're either both positive. So let's just rewrite this. So case 1, they're both positive. So k plus 5 greater than 0 and k minus 3 greater than 0. So that means k is greater than minus 5, and at the same time, k is greater than 3. And we said if we drew this, if we had 0 there, minus 5 would be down here, and 3 would be up here. If we want k to be greater than 3 and greater than minus 5 at the same time, then if it was anywhere in here, it would only be greater than minus 5, but we need to include k is greater than 3. So anywhere in here is off limits. We can't do that. Anywhere down here is off limits because it's not greater than 5 or greater than 3. So we have to pick up here because it's and. So this is greater than 3 and it's greater than 5. So let's pick that. So we can just choose this one on its own. So k greater than 3 already includes everything greater than 5. So if it's greater than 3, it's everything. If k is greater than 3, it's already greater than everything that's greater than minus 5. So we can reduce these two equations here down into 1. And we'll do the same for case 2. So case 2 is they're both negative. So k plus 5 is less than 0, and k minus 3 is less than 0. So that means k is less than minus 5, and at the same time, k is less than 3. So we can do the same thing, minus 5, 0, 3. So if we want to be less than minus 5, so everything down here, and less than everything down here. So this is off limits. Everything in here is off limits. Where they overlap, that's where we want. So that's where k is less than minus 5. So that is the same as writing this. So this is the one we're going to take. And now we have the two cases, so we're going to combine them. So this one and this one, going to combine the two of them. So k greater than 3 and k less than minus 5. So this is actually the same as k, minus 5 greater than k, and k greater than 3. If you write them on top of each other like this with the k, it makes it easier, so then you can just smash the k's together. K is greater than 3 and less than minus 5. And it doesn't matter which way you write it, you can say that way as well. So k is greater than 3 and less than minus 5. And that is your final answer. So we were trying to determine the values of k for which the quadratic expression here has real roots. So that's what we imposed here. So this is where it has real roots, and then we found the values for k for which this is true. So when k is greater than 3 and less than minus 5, I'll even copy this down here. Copy, paste. So when 3 is greater than, or when k is greater than 3 and less than minus 5, then b squared minus 4ac of the equation we started with is greater than 0, and therefore real roots. So real roots when k greater than 3 and less than minus 5. That's your question done. Great. So on to the next question. So question 2 says, construct a quadratic equation with roots 3 and 7 expressed in the form ax squared plus bx plus c. Okay, well, if our roots are 3 and 7, that means x minus 3 is a factor. Well, let me start from the very start. So if x and 3 and 7 are roots, that means x is equal to 3 and x is equal to 7. And if we sub these into our quadratic expression that we're going to make, everything should be equal to 0. But this also means that if we bring the 3 to the other side, x minus 3 is a factor of the quadratic expression, and x minus 7 is a factor. And if we multiply these together, we'll get our quadratic expression. So factors multiplied together give the equation, roots subbed in give 0. So x minus 3 times x minus 7, that's going to be x times x is x squared, x times minus 3 is minus 3x, and minus 7 times x is minus 7x, minus 7 times minus 3 is plus 21. And we can add these together, so that's x squared minus 10x plus 21. Now, the reason I put this question in is because of the trick I was telling you before. So you can write any quadratic expression that's written like this, x squared plus bx plus c, we can write that as x squared minus x times a plus b plus a times b. And a and b here are your roots. So you can write any quadratic expression like this. And this is kind of useful because we'll see in an exam question coming up, it gives us information about the roots that we can just find straight away without having to factorize or sub in or trial and error, anything like that. We can just find the roots straight away and do it that way. So if I was to, so we made this expression appear out of these roots. So let's see if I can write this like this and then see if it's the same roots. So this is x squared minus x times 10 plus 21. That's x squared minus 10. And obviously, that's 3 plus 7 plus 3 times 7. And these are our roots. So x is equal to 3 and x is equal to 7. So it's just a small thing. It helps you with some questions. Just remember this minus here. That's the bit that'll catch people out. If we had up here, if we had plus 10 instead, and we wanted to write it like this, we'd have to do x squared minus x times minus 10, because then a negative times a negative is a positive. So just be careful with that. But yeah, on to the next question. Next question is similar. So construct a quadratic equation with roots 2 and 2/3 expressed in the form ax squared plus bx plus c. Well, we can just jump straight away to our new equation, x squared minus x times a plus b, and then plus a times b, where a and b are our roots. So let's just do x squared minus x times 2 plus 2/3 plus 2 times 2/3. So x squared minus x times 6 over 3 plus 2 over 3 plus 4 over 3. And that's x squared minus x plus 8 over 3 plus 4 over 3. And that is our expression. And so the reason I did this was because you can see this could be kind of awkward when we do x is equal to 2 over 3 and then x minus 2 over 3 is a factor, and then multiply that by x minus 2. You have to multiply by fractions. I don't know, it's just a bit tricky. It might take a while. This, I'm just showing you like other ways of doing it. So this is your final answer. So yeah, on to the next question. So this is the exam question where I was saying it might be useful to remember what we were doing here. So, but let's just run through it and see where we can apply it. So x squared plus 5x plus p, where x is a real number, so that could even be 2.3789. So any kind of number, it can even be root 2. And p lies between 8 and minus 3 and is an integer. So an integer is either 1, minus 1, 2, minus 2, 3, minus 3. So whole numbers, positive and negative. So that's what p is. So this could be useful if you get, so we're trying to find values for p here and here. And if we get anything that's a decimal, we know we've gone wrong somewhere because p needs to be a whole number. But anyway, let's get into the question. So find the value of p for which x plus 3 is a factor of f of x. So if x plus 3 is a factor, that means x equals minus 3 is a root. And when we sub in roots, we get 0. So I'm just subbing in everywhere I see x, I'm subbing in minus 3. And then we're going to let that equal to 0. So minus 3 squared is just going to be 9. The minus times a minus is a plus. 5 times minus 3 is minus 15. And then just p is p. And then 0. And now we can bring the 9 across to this side and the 15 across to that side. And we're going to see that p is going to be equal to 6. And that's your final answer. So when p is 6, x plus 3 is a factor of f. And x minus 3 is a root. That's basically what we're saying. But yeah. So I'll just write that away. Find the value of p for which f of x has roots which differ by 3. So now, instead of p equal to 6, that means x minus 3 is a factor. Now we're trying to find the value for p for which the roots differ by 3. Now, this is kind of tricky because some people get caught out because we saw that x minus 3 up here was a root, but these are different roots. Basically, we're trying to find roots that are when they differ by 3. And so people got thrown off that year by this. But let's just kind of ignore everything up here. We're trying to find a different value for p. And what we're trying to do is find a p for which the roots differ by 3. And the way we can do that is this is our original expression. If we write the one we wrote earlier, then we know every quadratic can be written like that. So, all right, this is a bit better, sorry. X squared minus x times a plus b plus a times b. We can see that, well, first let's rewrite. Let's get this kind of in the same form. So x squared minus x times minus 5 plus b. So we can see that this is minus x minus x. That means minus 5 is going to be equal to a plus b, and p is going to be equal to a times b. So let's write those. A plus b is going to be minus 5, and a times b is going to be p. So now we're trying to find p. This is kind of similar to, you see these are simultaneous equations. But in the second one, we don't have a plus. So we're going to have to do the simultaneous equation method where we sub in instead of cancelling. But we still have a bit of information that we haven't used. We need to find that the roots differ by 3. So if they differ by 3, then a minus b is going to be equal to 3. And we can see that a is going to be equal to 3 plus b. And now we have an equation for a that we can sub in and find values. So I'll just write this over to the side. If a is equal to 3 plus b, if I sub this into here, then 3 plus b, so that's what a was, 3 plus b, and then we're adding b, and that's going to be equal to minus 5. So then 3 plus 2b is going to be minus 5, 2b is going to be minus 5 minus 3 is minus 8, b is going to be minus 4. And so now we have a value for b, we're trying to find a value for a, and we can sub into our second one. So a times b is going to be p. Oh no, sorry. We're trying to find a value for a, so we're going to sub in here that we used. So a is going to be 3 plus b, so that's going to be 3 minus 4, so it's going to be minus 1. And so now we have a value for a and a value for b, and this is exactly what we need to find p. So a times b is equal to p, so we found a was minus 1 and we found b was minus 4 equal to p, so p is going to be 4. That's your final answer. So when p is 4, f of x has roots which differ by 3. And that's the full question done. So you can see, if we didn't know, we could write our equation like this, and just compare terms like this, you can see that it'd be a lot trickier to find like the roots that we need to find that are different by 3, and then and find p from that. It's just a bit trickier. This way is a lot easier. But yeah, on to the next question. So on to the next question. So it says find the range of values of x for which the absolute value of 2x plus 5 minus 1 is less than 0 or equal to 0, where x is just any number. So I threw this question in because we're continuing our theme of inequalities. That's what these are called. So things less than 0, things greater than 0, things greater than or equal to 0 that we saw when we were doing the discriminant. And that leads to things like case 1, where we saw things are both positive, things are both negative, and case 2, it's just a bit tricky to wrap your head around sometimes. But continuing on from that, we see another thing that we haven't seen before. So this is actually called the absolute value. And so briefly, I'll describe what the absolute value is. The absolute value can basically be described as the distance a number is from the origin. So if we have our number line here, and we have 0, minus 2, and 2, the absolute value is basically how far away, oh, sorry, that's positive 2, is basically how far away 2 and minus 2 are from 0. So if we take the absolute value of 2, that's going to be the distance from 2 to 0. And you can see if that's 1, that's 1 space, 2 spaces. And if we do the absolute value of minus 2, that's the same thing, minus 2 to 0. That's going to be 1 space, 2 space. So the absolute value, basically what it does is turns any negative number into a positive number, because distance can't be negative. There's always some kind of distance between minus 2 and 0. So that's basically, if you can remember this, you don't have to remember like the description of absolute value, and they won't ask that, but do remember this, that absolute value basically turns any negative into a positive. But yeah, so we're going to use this and we're going to solve this. Okay, so find the range of values of x for which 2x plus 5 minus 1 is less than or equal to 0. So if we even rewrite this, we can bring our 1 across straight away. So 2x plus 5 is less than 0 in the absolute value. So I might just, let's go through it again just to see what this means. So remember, the absolute value is the distance from the origin. So if we have 2x plus 5, and that's positive, and we have minus 2x plus 5, the absolute value means it's the distance to the origin. And these two distances will be the same. But we want the distance from the origin to be less than or equal to 0, or to 1, sorry. So if this is 1 and this is minus 1, then here you can see that the absolute value, this here, is less than 1. And we can even exclude it up all the way up until it's equal to 1. So basically, this is what it's going to look like visually. So 2x plus 5 is going to be somewhere between 0 and 1, and minus 2x plus 5 is going to be somewhere between minus 1 and 0. And basically, all that can be represented just in one line of maths, and that's why the absolute value is useful. But the reason I'm showing you this is because basically this lets us rewrite this up here into an easier inequality. So if positive 2x plus 5 is less than 1, and minus 2x plus 5 is greater than minus 1, then we can rewrite this up here as 2x plus 5 less than or equal to 1 and greater than or equal to minus 1. Because this here, 2x plus 5 less than 1, and it's greater than or equal to minus 1. So that's why I told you this trick during the grind, but this is kind of the reason behind it, because the distance is less than 1, and when it's greater than minus 1, it's up here. So yeah, and not something you need to remember, but do remember this step up here, turning this into this. So yeah, when you have absolute value, you're going to bring your 1 over here and change it to minus 1. And now we can just solve it like this. So if we bring our 5 here and our 5 over here, that'll be 2x is less than 1 minus 5 is greater than minus 1 minus 5. So it's minus 6 is less than 2x is less than 1 minus 5 is minus 4. So now we can divide everything by 2. So x is less than minus 2 is greater than or equal to minus 3. And that's your final answer. So what this means is if minus 3 is here and minus 2 is here, x lies somewhere in here with minus 2 and minus 3 included because it's less than or equal to. So basically, we're trying to find the range of values. We did that. So anywhere between minus 2 and 3, then if we sub in any value between minus 2 and 3 for x, then when all this works out, even if it's minus, the absolute value will turn into a plus, and then that'll be less than 1. So that's basically what we found, and that's the whole question done. So find the range of values for which absolute value minus 1 is less than 0, x lies between minus 2 and minus 3. That's the question done. So yeah, moving on, we moved on to a bit of logs, and we'll jump into those now. So moving on, we moved on to logs, and basically I'll do a brief description of logs. So logs, think of logs as the opposite of indices. So the log of something, x, is going to be the opposite of x to the power of 2, say. And that's log to the base 2. So log to the base 2 of x is going to be the opposite of x to the power of 2. And the same thing for log base 3 of x is going to be opposite to x to the power of 3. And you can keep going like that. Basically, this is how logs were defined. And that's how it was found. This is why it's kind of hard to explain to people what logs are, is because basically when logs were discovered or invented, they basically just defined it as the opposite. They just said, well, we have this thing where x is going to be squared or x is going to be cubed. It would be nice to have something that will do the opposite of that. And that's basically what they did with logs. But the best way to understand it is just to kind of go through some examples, which is what we did. And I'll just run through some briefly here. So say we had 3 to the power of x is equal to 27. Basically what logs ask is 3 to the power of what is going to give me 27. And the way we can do that is if we take log to the base 3 of x and then log to the base 3 of 27, because we have to do it to both sides of an equation. What we defined was that log to the base 3 is the opposite of log to the 3 of x. So these can actually cancel, and we're left with just the x. And then log to the base 3 of 27 is we can just put that straight into our calculator, and we're going to get x is equal to 3. So a handy way to remember logs is asking the question 3 to the power of what gives us the number on the right hand side. So if we keep going, if we said 7 to the power of something was equal to 49, how would we find this? Well, we'd get log to the base 7 of 7 to the power of x and log to the base 7 of 49. These would cancel. We'd bring our x down, and this is just a number, and you put that into your calculator, you end up with 2. So 7 to the power of 2 is actually going to be 49. And that's basically what logs lets us do. In your log tables, there's actually lots of formulas as well that we'll use, and we'll see that in the very next question that we'll do. You don't have to learn these off, because the more you use them, the more you'll just remember them. But some brief ones that are useful is if you have log of something times another thing, that's the same as log plus log. And if you have log of something divided by something, that's the same as log minus log. And very last one, probably that you'll need the most often, is log of anything, like to the power of anything else. That's going to be the same as the power times the log of a. So how I would describe this is basically just bring the p down and multiply it in. So they're kind of the main three that you need, and we'll see that in the next question. So our last question says, given log to the base a of 2 is equal to p, and log to the base a of 3 is equal to q, where a is greater than 0. Oh yeah, that's another rule of logs. You can't have logs of minus numbers. And you'll see that if you just mess around with your calculator and plug in things like that, you'll come to the same thing. But that's just a rule. You don't really need to remember it. But okay, so write each of the following in terms of p and q. So log to the base a of 8 over 3. Well, if you go to your log tables, you'll see that we have a rule for things divided by each other, and that's going to be one minus the other, or the top one minus the bottom one. So it's going to be log to the base a of 8 minus log to the base a of 3. And we also know that log to the base a of 2 is going to be p, and log to the base a of 3 is q. Well, we have log to the base a of 3 already here, so that's going to be log to the base a of 8 minus log to the base a of 3 is just q. And now we need to turn this into a p somehow. And the way we have a 2 is equal to p, so we're going to have to turn this 8 somehow into something related to 2. Well, that's kind of easy. You can see that log to the base a of 2 cubed is going to give us 8. That's minus q. And then we have another rule in our logbook that says something to the power of something. We can just bring the 3 down and multiply it in. So that'll be 3 times log to the base a of 2 minus q. And we know what log to the base a of 2 is. It's just p. So this whole thing is just going to be 3p minus q. And that's your final answer. So if this question came up in the LeamCert, I'd be very, very happy. It's just a couple lines. You could even skip some of these steps if you wanted. And yeah, by the time it comes around to it, you'll be really, really happy to see these. It might not make sense at the minute, but and you might not have a hard time remembering the laws, but the more you use them, the more they'll stick in your brain, and the more you remember them. But yeah, so very last question. We're doing the same thing here, but with a slightly harder exponent. So log to the base a, we know something divided by something. We're just going to minus it off each other. So log to the base a of 9a is going to be log to the base a of 16. And okay, so we have another rule, something multiplied by each other is going to be added. So log to the base a of 9 plus log to the base a of a squared and minus log to the base a of 16. So now we have everything kind of laid out. We can see that this one straight away, log to the base a is going to be the opposite of a to the power of anything. So that's just going to leave us with 2. And I'm just rewriting everything. And now, how are we going to turn these into p and q? Well, we know what log to the base 2 is and log 3 is. So we need to somehow turn 9 and 16 into something to do with 2 and 3. Well, that's kind of easy. If we see 9 is 3 squared, and then 16 is 2 to the power of 4, well then we can use our rule that you bring the 2 down. That's 2 log 3 plus 2 minus 4 log a2. And we know what those are. That's 2q plus 2 minus 4p. And that is your final answer. You could even bring the 2 out if you really wanted. So that's q plus 1 minus 2p. But you don't need to do that. But that's just something. But yeah, that's your final answer. And that's the whole question done. So those are handy marks, logs. You don't think you have to learn these things off. Like I've said this enough, but they really do just come to you the more you use them. But yeah, so those are all the questions we ran through in the grind. As always, if I've forgotten any, let me know. But yeah, I'll see you at the next grind.